In this video, I will show you how to find a mathematical model of this wheel, which has a mass on the side here. This wheel here has a inertia, and we assume that this mass is a point on the edge of the wheel. We'll use the kinetic and potential energy in order to find how this wheel moves around. So first, we want to find the position of the center here as a function of theta. So let's call that x. So x is equal to r multiplied by theta. And this is only moving in the x direction, so we can just put a I hat here. So we assume that the position x is in orgo. And the speed of this point would therefore be the speed, or just the derivative of x. Now I want to find the position here, which we can call p. So p at time 0 should be equal to, so the sine of theta multiplied by r is this part. So that is in x direction, so we just say r multiplied by sine theta. And then this part here is the y direction. So then we have r multiplied by cos theta. So this is p0. Now p is just equal to p0 plus x. So we have x, or we can just write it out. So r. And then we have theta plus sine theta. And then we have r cos theta. So we also need the p derivative. So basically the speed of the mass. And this should be equal to r. And then it's 1 plus cos theta. And then minus r sine theta. So I just took the derivative of p. We want to save these for later, so I just put it here. So now I want to find the kinetic energy. So the kinetic energy first of the wheel. So call that TW. So now I want to find the kinetic energy. So we just start with the wheel. So I call that TW. So first we have the rotational kinetic energy, which is 1/2 multiplied by the inertia times the derivative of the angle squared. And then we have the translational kinetic energy, which is 1/2. And then the big M is the mass of the wheel in itself. And then x dot squared. So this wheel is a kind of like a circle without inner mass. So the inertia would therefore be m r squared. So if we rewrite the kinetic energy of the wheel, we get that 1/2 and then m r squared multiplied by theta dot plus 1/2. And then we have m. And then if we remember, x dot is equal to r theta dot. So we have r squared theta squared. So this is just equal to m r squared theta squared. Now we want to find the kinetic energy of the mass. So that is Tm. Since it doesn't have any inertia, we just don't have any rotational energy. That means that the energy is equal to 1/2, then multiplied by the mass. And then we have P dot transposed multiplied by P dot. So this should be equal to 1/2 multiplied by the mass. And then this part here is just this part squared plus this part squared. So we can first do the first part. So it's r squared multiplied by 1 plus cos theta. And this one squared as well. And then we have plus r squared sine squared. Squared. Like that. We would therefore get 1/2 and then m again. And then if we solve this, we get r squared. And then we have this part multiplied by this part, multiplied by 2. So this is 2, and then cos theta. Yeah, and we also need to add the r, so I just added it here. And then 2r theta. So we still have the r squared as well. And now we get 1 squared plus 2 cos theta plus cos squared theta. And then we have the other part remains the same. If you look closely, you can see that we have r squared multiplied by cos squared. So r squared cos squared plus r squared sine squared is equal to r squared. So that means we have still 1/2 m. And then we have r squared plus r squared 2 cos theta, and then plus r squared. This could therefore be written as, so we take the 2 out and the r squared out. So it leaves us with m and then r squared. Then we have 1 plus cos theta. So this leaves us with the kinetic energy of the wheel and the kinetic energy of the mass. So in order to get the total kinetic energy, we just add these two together. So we get that, yeah, so we can take r squared outside, and then we have m theta dot squared plus m1 plus cos theta. Now I want to find the kinetic energy. So the kinetic energy of the wheel itself remains constant because the road is flat, but the kinetic energy of the mass is changing. So we want to find that. So V should be equal to, so we have the mass multiplied by the gravity constant. The height of the mass is just the y coordinate of the position. So we can just add r cos, or multiply by r cos theta. Now I want to use the Lagrangian formula, which is this one, where the Lagrangian is equal to T minus V, so the kinetic energy minus the potential energy, and the Q is in this case equal to theta, because that's the only variable that we have. I now see that I forgot a theta dot squared on the kinetic energy, so I just add that. So first we want to find the Lagrangian derivative by theta dot, which is here. So this should be equal to the derivative of these two with respect to theta dot. So you can see that the potential energy doesn't have any theta dot. Therefore, we only need to look at the kinetic energy. So this should be equal to, so if we take the derivative of the first part, this one, this is r squared, and we still have m. We just take the derivative of theta dot squared. So we get like that. And this part is constant, so it just disappears. And then we have this part last. So we still have r squared, so plus r squared, and multiplied by m, and then multiplied by cos theta, and then we take the derivative, so it's multiplied by 2 theta dot, like that. Now when we take the derivative of this with respect to time, we first take the derivative of this theta dot, and then the cos theta. So this should be equal to 2r squared m, and then plus r squared m cos theta, And then the derivative of, yeah, I forgot a 2 here as well. Then the derivative of theta dot, which is theta double dot. And then we take the derivative of this cos theta. So then we get minus, and then sine theta multiplied by r squared m, and then 2 theta dot. Now we want to find this one, which is equal to this. So we can see that this part here is not dependent on theta. So we need to take the derivative of the last part here and the potential energy. So the derivative of the kinetic energy should be equal to r squared, and then multiplied by m, and then theta dot squared. And then we take the derivative of the cos theta, which is equal to sine theta, and then with a minus sign in front. And then we take, because there's minus the potential energy, we take minus the derivative of the potential energy as well. So we have m g r, and then the derivative of cos theta, which is sine theta with a minus in front, which gives plus. I'm sorry, but I also forgot this, that it's not constant. It is multiplied with a non-constant variable, so we have to add that as well. So we just add it here. So 1 plus cos theta, and yeah, we also have to add it here. So 1 plus cos theta. It disappears here and here because it's not dependent on on theta. So this is the equation you get when you solve this equation for the theta double dot. So theta double dot is actually all you need to model this wheel with a mass. And you also need the initial conditions, because you can just integrate to get the speed of the wheel, and you can integrate again to get the position of the wheel. You of course also need to convert, in order to find the position of the mass and the center of the wheel, you also need these equations here, with also the speed and the speed of the mass.